Let us explore the theory of infinite sets. We are going to talk about something called cardinal arithmetic in the context of infinite sets. And to start with that, let's look at some interesting sets that we have been discussing so far, and can we count them in a precise way. And although we are in infinite zone, is there a way to list infinite sets? Say here is the first element, second element, third element, and so on. And are there sets, are there infinite sets for which even this listing is not possible? And this is important before we get into the specifics. Let's look at this. Let's work with, say, the set of integers. And now that we have shown this and the natural numbers are of same cardinality, whether you work with natural numbers or integers, it is one and the same. The argument that you observe or you bring out in the context of natural numbers, it is also true in the context of integers. So the fundamental question is this. When we talk about binary relations in the context of finite sets, we have the set A, then we talk about A cross A, then we talk about a relation which is a subset of A cross A. Now let's assume A is infinite in nature, say it is I. If that's the case, what can we say about the cross product, and what can we say about a relation which is a subset of this? So to count how many relations are possible, what is the size of the cross product, simple answer is this is infinite, so this is infinite, this is infinite. But can we say something beyond? So that brings the following. Counting in the context of infinite sets. So here is a way to look at this concept. So we talk about something called countable sets or countable infinite sets. We also talk about something called uncountable infinite sets. So in the context of finite sets, so we say if there exists a bijection from say 1 to k to the set A, then cardinality of A equals k. Correct? You come up with a bijection from this set, the set which has got k elements, to the set under consideration, then you conclude cardinality of A is k. So similar thing is what we want to establish in the context of infinite sets. So we say a set is countably infinite if there exists a bijection from n to A, then A is countably infinite. So let's assume A is an infinite set. We want to know, does this set have any special property? We say it can be counted, or we say it is countably infinite when you get to see a bijection from n to a. And if no bijection exists, if there does not exist a bijection from n to a, then a is uncountable. What is this telling us? Suppose you say a set is countably infinite, what advantage are we getting? Suppose a set is countably infinite, then you see that there is a bijection from the set of natural numbers to the set. You get to see that 0 is mapped to this and so on. This gives you an ordering. This tells you here is the first element, here is the second element, here is the third element, and so on. So you are able to list or you are able to enumerate. So listing or enumeration is possible for a countably infinite set. And if it turns out that it is uncountable, then such a listing is not possible. Such an enumeration is not possible. So this gives you like when you have a bijection in the context of finite sets, you can say the first element is 1 that is mapped to 1, second element is 1 that is mapped to 2, and the last element is 1 that is mapped to k, or kth element is 1 that is mapped to k. We want a similar scheme in the context of infinite sets. Can you talk about the first element, second element, and 10th element, 100th element, and so on? Answer is yes. You won't be able to say here is the cardinality and the size of this is so much, but they are of same cardinality. And given an element here, I can give you the corresponding element in the codomain. Given an element in codomain, I can give you its pre-image. So one can list them in a systematic way. And that is quite interesting. And although they are infinite, you are able to differentiate that here is a set that can be listed, countably infinite set. Here is a list, here is a set that can be enumerated, countably infinite set. And this set, something that is uncountable, even such a listing is not possible. Okay. Now, are there countably infinite sets in computer science? Are there countably infinite sets in the field of mathematics? Are there uncountable sets in the field of computer science, in the field of mathematics? All that we shall see next. The definition itself brings n, so which means n has got a listing. So n is countably infinite, and n and I has got a mapping. So I is countably infinite. So it's easy to see that the base set is n and I. So now questions, what about the rational numbers? What about the real numbers, the set of real numbers? And questions, how many different inputs are possible? How many different computational problems are possible? Are these sets falling into this or this? Which we shall discuss next. Suppose the underlying set is the set of natural numbers, which we know it is countably infinite set. A cross A refers to n cross n. Now the question is n cross n countably infinite, or is it uncountable? So to talk about this, suppose I want to establish that it is countably infinite, all that we need is establish a bijection from n to n cross n. Correct? Suppose we come up with a bijection between these two, then it is countably infinite. If no such bijection exists, then you say it's uncountable. So remember, n cross n consists of pairs. So you have a comma b such that ab belongs to n. Correct? So something like you have got 0 comma 0, 0 comma 1, 1 comma 12, and 2 comma 15, 100 comma 120, and things like that. So now, is there a way to systematically list these pairs? If we can and establish a bijection to n, then we are done. Then it means n cross n is countably infinite. Yes, we'll see this. Cross product can be listed like a matrix, something that we have been using it at many places. So what we will do is, let me list one n on this side, 0, 1, 2, 3, 4 and so on. And on this side, I again list 0, 1, 2, 3 and so on. And this will tell you 0, 0, 0, 1, 0, 2 and so on. This will tell you 1, 0, 1, 1, 1, 2 and so on. This will tell us 2, 0 and so on. Like this it goes. Now what we will do is the following. Now we want to count this. Can we establish a bijection from this set? It covers everything. It covers all of n cross n to n. Here is a way to do it. What I will do is the following. Let me map this one to, say, 0th element, and let me map this one to first element, meaning I am going to proceed like this. Then let me map this to 2, which means from this I'll come like this. Then let me map this one to third, which means I'll come down. Then I'll go up. Then this is mapped to 4. Then you go up. Then you take right. Then you come down, come down, come down. Then like this. So this is precisely what we will be doing when we traverse this A cross A. So I am giving you a scheme using which you can list these in a specific order, because one has to establish, here is a way to list, one has to establish listing enumeration. I am giving you one approach. So this tells you the following. On one side you have n, on the other side you have n cross n. So what we say is the following: 0 comma 0 is mapped to 0, then 0 comma 1 is mapped to 1, then 1 comma 0 is mapped to 2, then 2 comma 0 is mapped to 3, which means the mapping is like this. So it's like this: you go layer by layer and ensure that all of this is completely mapped before you go to the next layer. And it's infinite in nature. So this side it's infinite, the other side is infinite. Although it's infinite, you can see them layer by layer, and you see that this kind of argument gives you mapping from n cross n to n. You give me an element in n, I can give you its map. You give me an element in n cross n, I can give you its pre-image. Okay, so that tells you n cross n is countably infinite. By definition, here is a bijection from n to n cross n. Therefore, the size of this is countable. It is countably infinite. Size of this set is countable, which means there is a specific way of listing this set. Okay, so now it is important that when you list, you follow this order. One should not list all this, then come back to this. That we should not do, because there is no end to this. It's infinite in nature. And similarly, one should not list all elements in column 1, then you go to column 2. It's not possible, because you don't know where column 1 ends. Similarly, you don't know where row 1 ends. But there is a clever way of visualizing this, that at each iteration you collect some finite subset of elements. Number of such iterations is infinite. But at this iteration, I map this. At this iteration, I map this. Then in the next iteration, I map this. Then in the next iteration, I map this. So like that, each iteration, you collect some finite elements and then map it. Then change your direction, go down and then go up, and things like that. Fine. Now this tells you n itself is countably infinite. It's infinite in nature. N cross n is much bigger. Of course, intuition. N cross n is much bigger than n as far as intuition is concerned. But logic says something else. Logic says n and n cross n are of same cardinality. This is precisely what we are interested in as part of this course. And now logic wins. Here is a formal argument that says n and n cross n are of same cardinality. And it tells you something beyond. It tells you that n and I are one and the same, and n cross n are one and the same, which means I and n cross n are one and the same. So like that, one can keep building this. And it tells you something more, that all countably infinite sets are of same cardinality. Because there exists a bijection to n, you can establish a transitive relationship. You can relate n and n cross n, and through that you can talk about that now there is a bijection from n cross n to this, and we also know there is a bijection from n to I. Therefore, this and this are of same cardinality. So you get to see that n cross n to this and this, that tells you that there exists a bijection from I to n cross n or n cross n to I. So such comparisons are possible among countably infinite sets. In fact, all of them are of same cardinality. And many interesting sets like this we shall discuss next.